Right now, while you are sitting on Earth beneath a sky that still looks familiar, a machine built before home computers became common is moving through a place no human being has ever visited. It is approaching a distance of one light day from Earth. A command sent from our planet must travel for almost 24 hours before it can reach the spacecraft, and its reply needs almost another full day to come home. There is no rescue mission. There is no repair crew. There is only a fading radio voice, a dish antenna, two surviving scientific instruments, and engineers trying to keep a machine launched in 1977 alive in the darkness between the stars. And then, against every reasonable expectation, Voyager 1 turned back. Not by reversing its flight, it is still escaping outward into interstellar space. What turned back was something more fragile and, in a way, more astonishing. Its orientation, its attention, and its voice. Thrusters that had been considered unusable since 2004 were brought back to life so Voyager could continue making the tiny movements needed to keep itself correctly oriented and maintain communication with Earth. The oldest active explorer in deep space looked home again. And what came back through that impossibly narrow radio beam was not a photograph. It was not a cinematic image of an undiscovered planet. It was not a message from another civilization. It was something quieter, measurements from the darkness between the stars. And those measurements challenged the simple picture scientists had carried for generations. Stay with me, because by the time this story is over, the phrase empty space will no longer mean what you think it means. Subscribe now if you want more stories like this. We're just getting started. Voyager 1 began its journey on September 5, 1977. Launched from Cape Canaveral during an era when televisions were heavy, furniture, long-distance telephone calls were expensive, and the idea of carrying the world's knowledge in your pocket belonged to science fiction, its original mission was not to leave the solar system. It was designed to visit Jupiter and Saturn, return its data, and survive long enough to complete a planetary tour that already seemed almost impossibly ambitious. The spacecraft itself was hardly enormous. Its central structure was comparable in scale to a small car, and its most recognizable feature was a large white high-gain antenna dish. It carried cameras, particle detectors, magnetic field instruments, plasma wave sensors, computers of microscopic capability by modern standards, and 3 radioisotope generators that converted heat from decaying plutonium into electricity. Voyager was not powerful in the way modern people imagine power. Its computers could process only a tiny fraction of what an ordinary smartphone handles today. And after nearly half a century, every watt has become precious. The spacecraft's generators now lose about 4 watts of electrical output each year, the equivalent of watching a small light slowly dim, year after year, with no possibility of replacing the bulb. But Voyager possessed one advantage that no modern machine can manufacture: time. It reached Jupiter in 1979 and revealed a planetary system more violent and alive than expected. Voyager observations helped expose active volcanoes on Io, one of Jupiter's moons. It returned close views of swirling clouds, enormous storms, faint rings, and moons that behaved less like dead rocks and more like worlds with their own geological histories. Then, in 1980, Voyager 1 passed Saturn, examining the planet, its rings, and its largest moon, Titan. That Saturn encounter determined everything that followed. Voyager 1's path was bent so it could make a close inspection of Titan, but that choice diverted the spacecraft upward, out of the plane where the planets orbit. From then on, Voyager 1 was no longer heading toward another planetary appointment. It was heading toward the dark. Here is where the first twist in the story arrives. Voyager 1 was built for a mission measured in years, yet it became a mission measured in human generations. The engineers who designed it could not have known what the internet would become. They could not have imagined smartphones, streaming video, social media, or artificial intelligence systems discussing their spacecraft almost half a century later. Some of the scientists now involved with Voyager were not alive when it launched. The machine has outlived technologies, careers, institutions, and many of the people who first sent it into the sky. In 1990, after its planetary cameras had finished their main work, Voyager 1 performed one of the most emotionally significant turns in the history of exploration. At the request of astronomer Carl Sagan and others, the spacecraft looked back toward the inner solar system and photographed Earth from approximately 3.7 billion miles away. Our planet appeared as a tiny point of light suspended inside a scattered ray of sunlight. The pale blue dot. Earth occupied roughly 1 pixel. Every war, every border, every empire, Every family. Every person who had ever lived, all of it existed on that nearly invisible speck. After completing the solar system family portrait, Voyager 1's cameras were switched off permanently to conserve power and memory for the instruments needed during its journey toward interstellar space. Voyager would continue exploring, but it would no longer show us space through pictures. From that moment forward, its discoveries would arrive as numbers, particle counts, magnetic field readings, waveforms, and faint radio signals. That distinction matters. When people hear that Voyager discovered something, they often imagine a hidden planet, a mysterious spacecraft, or an unknown object captured on camera. But Voyager 1 cannot simply turn on a modern telescope and send back a crisp image. Its greatest discovery today is not something it saw. It is something it felt. For decades, scientists pictured the sun as existing inside an enormous protective bubble called the heliosphere. The sun continuously releases the solar wind, a flow of charged particles that expands far beyond the planets. That outflow inflates a vast region around our solar system and helps separate the environment generated by our sun from the interstellar medium, the thin plasma, dust, magnetic fields, and energetic particles occupying the space between stars. From Earth, this boundary is almost impossible to imagine. You cannot look into the night sky and see it. There is no bright shell surrounding the solar system. Yet, the heliosphere is part of the invisible architecture around our planetary home. It influences the energetic particle environment through which Earth and the other planets travel. Think about what that actually means. Earth's atmosphere protects your body from the vacuum of space. Our planet's magnetic field helps shield the surface from charged particles. Far beyond those defenses, the sun's influence creates another immense layer in our cosmic environment. Voyager 1 was traveling toward the place where that solar influence met the galaxy outside. Scientists expected a boundary. They expected changes in the populations of particles. They expected Voyager to move from one magnetic environment into another. In the simplest version, the heliopause, the outer boundary of the heliosphere, would behave like a coastline. On one side, the solar ocean. On the other, the interstellar sea. But nature did not give them a clean coastline. On August 25, 2012, at approximately 122 astronomical units from the Sun, Voyager 1 crossed the heliopause and became the first human-made object to enter interstellar space. 1 astronomical unit is the average distance between Earth and the Sun. Voyager had traveled more than 120 times that distance. Particle measurements recorded a dramatic fall in particles associated with the heliosphere and a major increase in galactic cosmic rays originating outside it. Those changes looked like the crossing scientists had waited decades to observe. Then, the magnetic field readings complicated everything. Many scientific models had predicted that the direction of the magnetic field would change abruptly when Voyager entered interstellar space. Instead, although the magnetic field strength increased significantly, its direction changed by less than 2 degrees. Voyager appeared to be surrounded by interstellar plasma, but the magnetic geometry did not behave like the clean diagram many scientists had expected. It was as though a ship had crossed from one ocean into another, but the compass continued pointing almost exactly the same way. The boundary was real. But it was not simple. Now, the story gets stranger. Voyager's plasma wave instrument began detecting oscillations in the charged material surrounding the spacecraft. Some of the strongest events were linked to disturbances that had begun at the Sun. Solar eruptions sent pressure waves outward across billions of miles. More than a year later, those disturbances reached Voyager's location and caused the thin interstellar plasma around the spacecraft to vibrate. Imagine striking one end of a structure so enormous that the vibration takes more than a year to reach the other side. Voyager could use the pitch of those plasma vibrations to estimate the density of the material around it. The result was astonishing. The plasma outside the heliosphere was far denser than the plasma Voyager had measured inside the outer solar boundary. The interstellar plasma surrounding the spacecraft had a density more than 40 times greater than the plasma measured in the heliosheath, the outermost region inside the heliosphere. Space between the stars was still extraordinarily thin by earthly standards. A laboratory vacuum on Earth could contain far more material, but interstellar space was not the absolute emptiness people often imagined. Then, researchers found something even more subtle. A faint, persistent plasma wave emission, a continuous interstellar hum. It was not an alien transmission. It contained no language, no mathematics, no warning, and no repeating beacon. It was the natural vibration of plasma, the charged medium through which Voyager was moving. Yet that extremely weak signal allowed researchers to trace the density of interstellar plasma more continuously, rather than waiting only for powerful solar disturbances to make the plasma ring loudly enough to measure. Analysis showed that the electron density around Voyager began rising in 2013 and reached levels roughly 40 times higher by the middle of 2015, remaining within a similar range with fluctuations throughout the dataset studied through early 2020. Stop and sit with that for a second. A spacecraft launched when disco music played on radios and personal computers barely existed was now listening to the physical texture of the space between stars. The probe was not merely surviving outside the heliosphere, it had become a moving microphone inside the local interstellar medium, and this is the discovery at the center of the story. Voyager found that the edge of the sun's domain is not a clean, silent wall. It is a complicated interaction zone. The interstellar medium contains variation, structure, and turbulence. The sun can send disturbances beyond the heliopause. Magnetic fields do not necessarily change in the simple way earlier models predicted. The boundary around our solar environment is dynamic, layered, and still not completely understood. That is what stopped the world. Not because every television station interrupted its programming, not because governments closed their offices, but because the implication stops anyone who truly understands it. Humanity had spent its entire existence looking outward from inside the sun's protective environment. Voyager was the first machine to step outside and touch the galaxy directly, and what it found was not an empty black ocean. It found weather. But the scientific triumph was nearly silenced. On November 14th, 2023, Voyager 1 stopped sending readable science and engineering information. Its radio carrier signal continued reaching Earth, so mission controllers knew the spacecraft was still alive and still receiving commands. But the information inside its signal had become unusable. To the mission team, it was like hearing a person speaking from another room, but every recognizable word had collapsed into nonsense. The problem was traced to Voyager's flight data subsystem, one of 3 onboard computers. This system is responsible for packaging the spacecraft's science and engineering information before transmitting it to Earth. Engineers discovered that a single memory chip had failed. The damaged area contained part of the computer code required to organize Voyager's data. That code could not simply be placed somewhere else as one complete block. No remaining memory location had enough empty space. So the engineers divided the affected code into smaller sections, placed those sections in different areas of the computer's surviving memory, and then updated the software references so the scattered pieces could continue functioning together. They were remotely reorganizing computer code inside a machine more than 15 billion miles away. Every command needed about 22.5 hours to reach Voyager at the time. The reply required another 22.5 hours to return. Every test was a conversation lasting almost 2 days. The repair worked. By June 2024, Voyager 1 had resumed normal scientific operations and was once again returning usable information from its instruments. The voice from interstellar space became understandable again. Then came another crisis. Voyager's thrusters are essential because they allow the spacecraft to control its orientation. The high-gain antenna must remain directed toward Earth so Voyager can receive commands and send back information. If that antenna drifts too far from its target, communication could be lost. Over decades, residue had been accumulating inside extremely narrow fuel tubes connected to the thrusters. Engineers needed another option before the active system became unusable. They turned to a set of roll thrusters that had been considered inoperable since 2004. This was the moment Voyager turned back in the most literal way the mission could still achieve. Not a U-turn toward Earth. Not a reversal through interstellar space. Voyager does not have enough fuel to cancel its outward velocity and fly home. Instead, engineers restored dormant thrusters capable of helping control the spacecraft's roll orientation. These tiny movements allow Voyager to maintain its attitude and keep its communication system correctly aligned. In 2025, NASA announced that the long dormant thrusters had been revived. A machine older than many of the engineers guiding it had recovered a capability lost more than 20 years earlier. Here is the twist almost nobody outside the mission talks about. Voyager's most dramatic modern achievement is not speed. It is precision. The spacecraft is escaping outward at approximately 3.5 astronomical units each year. Yet it must remain oriented accurately enough for its faint transmission to be detected by enormous antennas on Earth. At Voyager's distance, Earth is not a giant planet filling its field of view. Earth is effectively a direction. A tiny target located near a distant star. A signal traveling at light speed still needs almost an entire day to cross the distance. That means mission control cannot steer Voyager in real time. There is no joystick. No engineer can observe a problem and correct it instantly. A command sent today may not produce a confirmed result until almost 2 days later. The machine and its team communicate like two people exchanging messages across an ocean where each sentence requires a day to arrive. But here's the part that stops being abstract and starts becoming personal. Voyager is running out of electricity. Its radioisotope generators weaken gradually as their plutonium fuel decays and their electrical components age. To preserve the mission, engineers have been switching off heaters, subsystems, and scientific instruments in a carefully determined order. In February 2025, Voyager 1's cosmic ray instrument was shut down. On April 17, 2026, NASA turned off Voyager 1's low-energy charged particle instrument. That left only two operating scientific instruments: the magnetometer, which measures magnetic fields, and the plasma wave subsystem, which listens to plasma oscillations. Both continue sending information from a region no other operating human-made spacecraft has explored. Each shutdown is practical. Switching off one system may give the remaining systems additional operating time. But each shutdown is also permanent in the emotional sense. A scientific sense that had been listening to the universe for almost half a century goes quiet, so the remaining senses can stay awake a little longer. Voyager is now approaching another milestone already locked into the calendar. On November 18, 2026, NASA calculates that Voyager 1 will be approximately 16.1 billion miles from Earth, the distance light travels in 24 hours. It will become the first human-made object to operate at a distance of one light day from our planet. A radio signal sent from Earth will require a full day to reach it. Its reply will require another day to return. Think about the absurdity of that. A machine built with 1970s electronics will be so distant that tomorrow's command will reach it the day after tomorrow. Its response will arrive another day later. Light can cross your kitchen almost instantly, but the radio instructions sent to Voyager will cross more than 16 billion miles of darkness before touching an antenna built when Jimmy Carter was president. And yet the spacecraft is still measuring. Its magnetometer continues sampling the interstellar magnetic field. Its plasma wave instrument continues listening to the charged medium surrounding it. These instruments do not produce glamorous pictures. They will not send back a photograph of Voyager floating beside an unknown star. But together, they are recording something no other active spacecraft can measure from the same location: the local interstellar environment beyond the sun's bubble. Come back to the science, because there is one more thing. The persistent plasma waves detected by Voyager imply that interstellar space contains variations in density across enormous distances. These variations are associated with interstellar turbulence, the movement and structure of ionized material between stars. Understanding that turbulence matters, because it affects how energetic particles move through the galaxy, how energy is transferred through plasma, and how radio signals from distant astronomical objects can become distorted or scattered. Voyager also showed that the sun's story does not end neatly at the heliopause. Solar eruptions can generate disturbances that travel outward and eventually interact with plasma outside the formal solar boundary. The sun can make the interstellar medium ring. That means the frontier is not simply a locked door separating solar from galactic. It is more like a shoreline during a storm, where waves, pressure, particles, and magnetic fields interact across a changing edge. Scientists are still trying to understand the true three-dimensional shape of the heliosphere. Is it broadly comet-shaped, with a long tail? Is it more rounded? Does it contain jets, lobes, ripples, or major asymmetries caused by the surrounding interstellar magnetic field? Voyager 1 crossed the boundary in one direction. Voyager 2 crossed it in another. 2 crossing points are scientifically priceless. But 2 points are not a complete map. This is why Voyager's remaining measurements are so important. There is no replacement spacecraft waiting nearby. There is no newer probe scheduled to pass Voyager next week and take over its work. Future interstellar probe concepts may travel faster and carry more advanced instruments. But the distances are so extreme that reaching the heliopause still requires years or decades. Voyager's scientific window is closing now. And now comes the quietest part of the story. Attached to Voyager 1 is a gold-plated copper record containing sounds and images selected to represent life on Earth. It carries greetings in different languages, music from several cultures, sounds from nature, scientific information, and encoded images. The golden record was never a practical attempt to contact extraterrestrials on a human timescale. Space is too large. The chance of accidental discovery is too small. It was a statement about us. We knew the spacecraft would eventually outlive its active mission. We knew it could outlive our present civilization. Long after its power fades, long after its transmitter becomes silent, Voyager 1 will continue moving through the Milky Way. In the year 40,272, it is expected to pass within approximately 1.7 light-years of a star known as AC plus 793888, also commonly called Gliese 445. By then, the constellations will have changed. Human languages may be unrecognizable. Continents will have moved. But the spacecraft will still carry the record. There is something almost unbearably human about that. We constructed a machine to study planets. When its main planetary mission ended, we allowed it to continue. We gave it our music. We gave it the sounds of waves, wind, thunder, animals, laughter, and heartbeat. Then we aimed it into a darkness we could not cross ourselves. And now, nearly half a century later, the machine is still turning its antenna toward home. It does not know Earth exists. It does not feel loyalty. It does not remember the engineers who assembled it. But through physics, programming, and extraordinary human persistence, it behaves like a traveler who refuses to stop writing back. The final discovery is not an alien object. It is not proof of another civilization. It is not a secret planet hidden beyond Neptune. The discovery is that the frontier itself is filled with structure. The space between stars possesses density, motion, magnetism, turbulence, and natural plasma oscillations. The sun's protective domain has a complicated edge, and the only instruments humanity has operating on its far side are slowly going dark. Several explanations remain possible for the patterns Voyager observes. Some variations may come from the natural turbulence of the local interstellar medium. Others may be shaped by solar eruptions that continue influencing plasma beyond the heliopause. With one aging spacecraft moving along one path, separating local galactic structure from distant solar effects is not always easy. That uncertainty is not a weakness. It is the point of exploration. Voyager crossed a boundary and demonstrated that the boundary was more complicated than our maps. The first traveler to reach a new ocean does not return with a finished atlas. It returns with evidence that the coastline is different from what everyone imagined. So, did Voyager 1 just turn back? No, not in the way the headline first suggests. It is not flying home. It will never return to Earth. Its outward interstellar trajectory is effectively permanent. But its dormant orientation thrusters turned back on. Its antenna continued turning toward Earth. Its readable scientific voice returned after engineers reconstructed damaged computer code from across the solar system, and the information it transmitted forced humanity to turn back toward its own assumptions, to reconsider the boundary around the sun, the meaning of interstellar space, and the belief that the darkness between stars is empty. That may be the most honest version of the story. Voyager did not stop the world with a scream. It stopped us with a whisper, a faint plasma hum carried across more than 16 billion miles. A signal from a machine built before the modern digital world existed. One day, perhaps during the next decade, its power will become too weak to operate even one scientific instrument. Later, the transmitter will fade. The Deep Space Network will listen, and nothing recognizable will return. There may be no explosion, no final photograph, no dramatic last sentence. The signal may simply disappear beneath the background noise. But silence will not mean failure. By then, Voyager 1 will have transformed from an active spacecraft into an artifact, from a scientific mission into a moving piece of human history. It will continue into interstellar night, carrying evidence that, for one brief moment on a small blue planet, a species looked upward, built something fragile, and sent it beyond the edge of the sun. And right now, while there is still electricity, while the antenna can still point home, and while two instruments can still listen, Voyager 1 is telling us what the galaxy feels like. Subscribe right now, drop a comment with the moment in Voyager's journey that means the most to you, and share this story, because the oldest active voice in deep space is fading, and this story deserves more than the silence it is heading toward.